Hello everyone, today we're going to be talking about functions. A function between two sets A and B is a non-empty relation on A and B that satisfies two key conditions. One, existence. Every element in A is related to an element in B. Or to be more formal, for every A in big A, there exists B in big B such that AB is an ordered pair that's an element of the relation F. Or in other words, f of A equals B for some B in big B. The second property needs to satisfy is uniqueness, which means that the value that f assigns to A is unique. Or to be more formal, if AB and AC are two pairs in F, then we must have B equals C. Or in other words, f of A equals B for a unique B. Let's go over some examples of what functions aren't. 1 over x is not a function from the real numbers to the real numbers because it's undefined at 0. When x equals 0, f of 0 is equal to 1 divided by 0, which does not exist. So we see this relation fails the existence property. It's worth noting that if we instead redefine the input for 1 over x as being the real numbers without 0 instead of just the real numbers, then it does become a function. Now let's take a look at another non-example. Let's define an inverse square root relation on the real numbers, defined by xy being a pair in the relation if and only if x equals y squared. For example, 2 square root of 2 would be in the relation, and 2 negative square root of 2 would also be in the relation. However, since this relation assigns two different values to x equals 2, we see that this relation can't be a function, because it fails the uniqueness property. Now for some additional terminology. We call the input set that a function f is mapping from the domain, and we call the set that f is mapping to the codomain. Also, it's important to note that f might not reach every value in B. For example, if we think about the function sine of x from the real numbers to the real numbers, then we see that sine of x can't produce every real number. It can only produce the real numbers in the range of -1 to 1. We define the image of f to be the set of values that f actually reaches. And we also denote the image of a subset of the domain as f of c, which represents the subset of B that C gets mapped to by f. More formally, it's the set of B in big B such that CB is a pair in F, for some C in big C. Also, note that the image of the domain A means the exact same thing as the image of F. We define the preimage of a subset C of the codomain B, denoted F inverse of C, to be the subset in A that gets mapped to C by F. In other words, it's the subset of A in big A such that AC is a pair in F, for some C in big C. Now let's test our understanding of functions with some practice problems. Number 1. If f is a function from A to B, and C is a subset of the domain A, then we need to show that C is a subset of the preimage of the image of C. First, we let x be an element of C. Then by the existence property of functions, f of x must be equal to y for some element y of the codomain B. But then this means that y has to be an element of the image of C, and hence that x has to be an element of the preimage of the image of C. Thus, we conclude that C is a subset of the preimage of the image of C. Note that in general we don't have full set equality here. This is because there might be elements that are not in C that get mapped to the image of C anyways. So there are some elements in the preimage of the image of C that aren't elements of C. Now let's move on to problem 2. Let f be a function from A to B, and let C1 and C2 be subsets of the domain A. Then we need to show that the image of the union of C1 and C2 is equal to the union of the images of C1 and C2. So first, we'll show that the left side is a subset of the right side. Let y be an element of the left side, the image of the union of C1 and C2. Then there must exist an element x in the union of C1 and C2, such that f of x equals y. If x is an element of C1, then y is an element of the image of C1. If x is an element of C2, then y has to be an element of the image of C2. Either way, y is an element of the union of the images of C1 and C2, thus showing that the left side is a subset of the right side. Now we need to show that the right side is a subset of the left side. Let y be an element of the right side. If y is an element of the image of C1, then there must exist x in C1 such that f of x equals y. If y is an element of the image of C2, then there must exist x in C2 such that f of x equals y. Either way, this x is an element of the union of C1 and C2. So this means that y is an element of the image of the union of C1 and C2. This shows that the right side is a subset of the left side, and combined with the earlier result, we know that the two sides are equal. Now let's move on to problem 3. Let f be a function from a to b, and let D be a subset of the codomain B. Then we need to show that the preimage of the complement of D in B is equal to the complement of the preimage of D in A. So first, we need to show that the left side is a subset of the right side. Let x be an element of the preimage of D in B. Then there must exist y in the complement of D and B such that f of x equals y. We have that x is an element of A by the definition of the preimage. We also know that y can't be an element of D, so that according to the uniqueness property of functions, x can't be an element of the preimage of D. Thus, since x is an element of A and it's not an element of the preimage of D, x is an element of the complement of the preimage of D in A. This shows that the left side is a subset of the right side. Now we need to show that the right side is a subset of the left side. Let x be an element of the right side. Then by the existence property of functions, f of x equals y for some element y of the codomain B. And since x isn't an element of the preimage of D, this means that y can't be an element of D. Since y is an element of D and not an element of D, y is an element of the complement of D and B. So x is an element of the preimage of D and B. This shows that the right side is a subset of the left side, and combined with the previous result, we know that the two sides have to be equal. Now, let's talk about some special kinds of functions. For a function f from a to b, we say that f is injective if for all a1 and a2 in big A, f of a1 being equal to f of a2 implies that a1 equals a2. We can visualize the function f as being a set of arrows that takes points in A to points in B. So we see that a function being injective means that multiple arrows can't point to the same element of B. A function can also be surjective, meaning that for every y in the codomain B, there exists x in the domain A such that f of x equals y. Or in other words, the image of A is B. If we again visualize f as being a set of arrows, we see that a function is surjective if there is an arrow pointing to every element of B. So the function f reaches every element of B. Also note that any function can be surjective if you just restrict the codomain to the points in B that f actually reaches. Finally, we say that a function is bijective if it is both injective and surjective. Bijective functions are functions that map the elements of A to elements of B one-to-one, meaning that elements in A and elements in B are paired up uniquely. Now, let's look at some statements that we can prove using these special function properties. Problem 4. Let f be a function from A to B, with C being a subset of the domain A. Then we need to show that C is equal to the preimage of the image of C if f is injective. We already showed that the left side is a subset of the right side in problem 1. And back then, we didn't even need to use the assumption that f was injective. Now we need to show that the right side is a subset of the left side. Let x be an element of the preimage of the image of C. Then this means that f of x equals y for some y that's an element of the image of C. This means there exists some x prime in C such that f of x prime equals y. F of x and f of x prime are both y, so f of x and f of x prime are equal to each other. And since f is injective, this means that x equals x prime, so x is an element of C. This shows that the right side is a subset of the left side, and combined with our result earlier from problem 1, we see that we have full set equality here provided that f is injective. Now, let's move on to problem 5. Let f be a function from A to B, with D being a subset of the codomain B. then we need to prove that the image of the preimage of D equals D, provided that f is surjective. We first need to show that the left side is a subset of the right side. This is pretty similar to problem 1, and you don't even need to use the fact that f is surjective. So I'll leave this as an exercise to you, the viewer. The more tricky part is showing that the right side is a subset of the left side, and for this part, we do need to use the fact that f is surjective. Let y be an element of D. Then since f is surjective, there exists x in the domain A such that f of x equals y. Since y is an element of D, we have that x is an element of the preimage of D, and so y is an element of the image of the preimage of D. This shows that the right side is a subset of the left side, and combined with the previous part, we have full set equality, provided that f is surjective. Now we're going to talk about some important consequences of bijective functions. We first consider the question of how do you tell if a function f is invertible? Or to be more specific, we're talking about an inverse relation f inverse, which is a subset of B cross A, and is defined as being the set of ordered pairs BA, such that AB is an ordered pair in F. And we want to know when f inverse is a function from B to A. The answer is that this happens when f is bijective. In order for the relation f inverse to be a function, it needs to satisfy the existence and uniqueness properties. F being surjective implies existence for f inverse because it guarantees that every element of B is related to an element in A, and f being injective implies that this A that each B is associated to is unique. Furthermore, when f is bijective, not only is f inverse a function, but f inverse is a bijective function. This is because the existence property of f implies the surjectiveness of f inverse, and the uniqueness of f implies the injectiveness of f inverse. Next, we're going to talk about function composition. Function composition is just the process of applying two functions in sequence. For example, applying a function f and then taking the result of that function and passing it on to another function g. We would express this in symbols by writing g circle f, which essentially means just passing f of x to g. Also, it might be a helpful exercise to verify that function composition is indeed a function, that it satisfies both the existence and uniqueness properties. An important property of function composition is that if both f and g are bijective, then this means that g of f is also bijective. Let f be a function from A to B, and let g be a function from B to C. We'll first show that if f and g are injective, then g of f is also injective. Suppose that g of f of x is equal to g of f of x prime for some x and x prime in A. Then since g is injective, we must have that f of x equals f of x prime. But since f is injective, we also have that x equals x prime. Hence, we conclude that g of f is injective. Next, we're going to show that if f and g are surjective, then g of f is also surjective. Let z be an element of C. Since g is surjective, we have that g of y equals z for some y that's an element of B. And since f is surjective, then we have that f of x equals y for some x that's an element of A. Thus, we found an element x such that g of f of x equals z, so we see that g of f is surjective. Combining all of this, we conclude that if f and g are bijective, then g of f is also bijective. Furthermore, when f and g are bijective, then the inverse of g of f is a function, and this inverse is actually equal to the composition of the inverses of f and g. This makes sense because g of f is the process of applying f and then g. So to invert this process, you first have to invert g, and then you have to invert f. So in this video, we managed to learn about what functions are, how to prove statements involving functions, and about special properties of functions. In the next video, we're going to look at how we can use bijections to develop a notion of size between sets, even infinite ones. But until then, thanks for watching. Don't forget to comment, like, and subscribe. Make sure you're all getting enough sleep. Bye-bye.